Welcome to this presentation of challenges with learning to program and problem solve, an analysis of student online discussions. I am Paul Piwek and will give this presentation together with my colleague Simon Savage. We are from the Open University in the UK. The Open University is a blended and distance learning university which was founded 50 years ago with over 2 million graduates so far. The research we will be talking about has been funded by the Institute of Coding. The Institute of Coding consists of 33 universities and over 100 employers across England and Wales, and is funded by the UK government's Department for Education. Let's start by identifying the problem that we've tried to address. When learning to program, students encounter a host of challenges and difficulties. They need to overcome misconceptions, threshold concepts, and acquire certain skills. As educators, we can do our work best when we know what these challenges are. There is an excellent literature on analyzing error messages and use of surveys, interviews, and questionnaires. See, for instance, the review on threshold concepts by Kate Sanders and Robert McCartney. But much of the data is based on after-the-fact recollections by students, rather than in-the-moment records of what actually happened when a student encountered a problem or challenge. This leads us to our approach. Our approach was to make use of online student discussions that happened when the students were facing a programming or problem-solving challenge. We took this approach to answer the following research question. What are the challenges that first-year distance learning students face when learning to program in Python? This study was carried out in the context of a blended distance learning module. Students interacted online with tutors and peers and also during face-to-face day schools. Materials included online activities, videos, simulations, and e-books, and there were also 3 printed books written specifically for the module. The module was aimed at first-year undergraduate students in computing and IT, but also taken by other, mainly STEM students. The module was specifically designed to prepare students for subsequent study. It focuses on critical thinking and problem-solving skills. About a third, 100 hours of study, were dedicated to problem-solving with Python. The cohort we studied has about 1,500 students, and student satisfaction for the module was very high, at over 90% satisfied with the quality of the module. Here, I'll hand over to my colleague Simon, who will say a bit more about student demographics and our actual findings.
Thank you, Paul. Right, as you can see here, our student demographic is different to a traditional university in that under 22s constitute only 11% of our cohort. Our biggest number of students is in the 25 to 39-year-old age bracket, being about 59%, but we also have a good number of students, about 6%, over 50 years old, including several who are over 65. Approximately 1/4 of our students are female. This is higher than the UK mean of 19% for computer science undergraduates, as identified by the UK Higher Education Statistics Agency. And as you can see here, about 10% of our students are not white. Now, 19% of our students have declared disability, and there may be well be more who have chosen not to disclose. Now, about a third of these students have declared mental health issues, and a quarter have specific learning difficulties such as dyslexia. Now, of course, the disabilities may not be mutually exclusive, with some students managing multiple conditions. Okay, now the module uses a variant of the Moodle virtual learning environment. This provides a forum facility which we use to host the Python Help Forum, whose purpose is to support students with their programming issues. The forum itself consists of a number of discussions as shown here. The black boxes are present to anonymise participant details. As we can see here, we've highlighted one set of posts which relate to defining flashcards. We call each thread a discussion, and each discussion consists of a number of posts contributed by multiple authors. We refer to them as speakers. Now, in addition to containing a post, we may have other media attached to the thread, particularly images. The post data was extracted from the forum and stored in a spreadsheet using custom Python script. Initial efforts to do this directly from the live site via some form of web scraping proved futile. It just took too long. So we took advantage of Moodle's facility to export forum data as HTML files and worked with those exported files. One of the Python script's jobs was to kickstart the anonymization process by replacing speaker name information with a code, and that was stored elsewhere in case we needed it. The extracted data was then sanity checked against the original and cleaned up for readability. For example, indentation of Python code embedded in forums wasn't always maintained during the export process, and this needed reinstating manually. This process also enabled us to continue the anonymization process. If we look at the final post on the screen here, you'll see two black boxes which contain name information that couldn't be automatically anonymized because it was the abbreviation of a full name. I should mention at this point that all data collection and analysis complied with approval processes and methods at the university, ensuring participant privacy, confidentiality and protection. Neither participants nor researchers received monetary or gift incentives. Also, permission was sought and given by speakers for extracts of their posts to be included. There is one exception to this, where we've chosen to paraphrase a conversation instead, since permission was not forthcoming. Here we'll look at the encoding process. We adopted descriptive coding achieved through an iterative process. We started by tagging posts with a topic type. They were also annotated with an emotion and a turn type, and we may return to analyse these at a later date. The next step was to rationalise the topic types and also to check them. For example, rather than having looping and iteration as separate topic types, they were all set to iteration. This did necessitate some further Python code to extract the topic types from a spreadsheet and do some calculations based on them. This was also useful for sorting out typos along the way. The topic types were then validated by a second person. This led to some further rationalisation together with a few tags being changed. Once all the topic types had been agreed, we carried out a thematic grouping which led to three high-level themes being identified: Python-related, problem-solving, generic programming-related, and module-specific issues. Based on this qualitative coding, certain quantitative information emerged, which I'll look at in a couple of minutes after highlighting a few reflections and limitations. First of all, the core data doesn't record the engagement of non-speakers. However, it does track the most read discussions, with the top 5 being read between 250 and nearly 400 times respectively. So we can be confident that some discussions are being read by potentially hundreds of readers. The manual nature of the coding process means that it may be biased by the encoder's choice of topic and turn type, although this is somewhat mitigated by team members reviewing the coding process and changes were made during that process. The forum's prime purpose was to support students in their understanding of Python concepts and problem-solving concepts raised in TM112. This means that topics beyond TM112 are unlikely to be raised, thus skewing the results in favour of TM112 related issues. The student cohort was constituted primarily of part-time distance learning undergraduate computing and IT students. Of course, their profile is likely to differ from, say, computer science students who may need support in different areas. And finally, the forum is unlikely to be the student's only point of support. We could reasonably expect them to use their tutors, other websites, social networking, etc. for support, and it's not possible to quantify the effect of this on our results. Okay. So, looking at a few statistics, the Python Help Forum contained 178 discussions with a total of 1,430 posts. 9 discussions containing 29 posts which were present which didn't fall within the scope of this study, such as one informing students of upcoming tutorials. These discussions have been maintained to ensure the completeness of data, but given the post type and topic type are irrelevant. Thus, there are 169 relevant discussions containing 1,401 posts. The encoding process identified 66 topics in the forum post spread across the 3 themes. We'll look at the distribution of these shortly, and when we do, it is worth noting that the first 1 or 2 topics in each theme are much more prevalent than the other topics in that theme. So, our first theme is Python-related topics. These are topics whose details are uniquely or significantly peculiar to Python in the context of the module. Similar topics may exist for other languages, but the specifics will vary dramatically. For example, configuring the Python IDE will be different to that for, say, Java or C++. Here we can see that questions related to the IDE are predominant in students' minds, followed by, in a poor second, by collections. We'll revisit these shortly. Problem solving and generic topics are those which occur across multiple programming languages and typically have the same details. For example, a typical problem solving workflow will be largely independent of the target programming language. Similarly, discussions about how to learn Python could equally apply to C, Z80 assembly, or even Fortran. Dominant here was the generic issue of students providing a code fragment and a problem. Behind this was bug finding, and in third, issues relating directly to how to learn Python. We'll look at examples of code fragments and bug finding in a moment. Module-specific topics are those whose focus is particularly related to the module and have little relevance outside of it. We won't explore these further here. Now, first one I'd like to look at is Python-related topics, particularly the IDE. Now, as we look through these coming slides, I should mention that much of the text is written by the students, so it does contain their typos too. The IDE was a topic raised in 24% of discussions. Prominent in these was confusion between how to use the idle shell and the editor. Idle is the standard default IDE for Python. For example, as shown here, a student experienced a syntax error with the code above. It transpires they had created the code in the shell, saved it as a Python file, and then tried to open it in the editor, causing all sorts of problems. Collections featured as a topic in 12.5% of discussions, with most discussions revolving around lists. Students seem to have trouble with indexing, confusing indices and contents, muddling up indexes and contents, inadvertently performing operations on lists rather than the contents of lists. Here we can see an example of the former, where a student is trying to add the values of the first and the last item in the list. They go through a number of variations, with the above being typical. They seem to appreciate that list 0 represents the first item in the list, however they still expect list last number to contain the last item, indicating they haven't quite appreciated the correct use of zero indexing. Okay. Looking at the problem solving and generic topics, code fragment problems were the most prevalent. Typically, these posts initiated a discussion where students knew they needed support, but in many cases the information provided was insufficient to receive targeted help, and indicated that they may not have the language confidence or knowledge to seek that support. Over 43% of discussions presented readers with a code fragment and a problem. Of these, about 12.5%, making it a quarter of all the code fragment discussions, related specifically to bug finding. For example, in the discussion shown here, which was titled to relate it to a quiz question number, the student did include a screenshot of part of their code and another screenshot showing the code runner feedback. In a different discussion shown above, we have something cryptically titled, "Where am I going wrong?" Note that the student didn't provide a diagram despite multiple requests for it. In both the example here and that on the previous slide, there is some confusion about which activity or quiz the student is referring to, although it can be deduced with some effort. The students omitting the code and not communicating their efforts at debugging leads to generic advice from peers. This was apparent in other threads too. However, in another quiz question query, a different student provides much more detail, including enough information to easily find the relevant material. The student has explained what they are observing and has tried to identify where the problem is. This quickly led to the problem being identified and targeted support offered by their peers. Now, let me hand you back to Paul to look at some conclusions.
Thank you, Simon. So to summarize, we found that many of the challenges we identified correspond with those in the literature, and a division into programming versus generic problem solving matches with themes identified by others, for instance, Kian and Lehman 2017. Now, the most frequent topics in our study seem not to be captured by previous studies, however. So for Python programming, in our study, these are challenges with using programming interfaces and tools. And for problem solving, this was how to actually ask a good question when a student's code doesn't work. This leads us to two recommendations. Firstly, we believe that use of several tools can add cognitive overload when students begin to learn programming, and so use of these tools should be dealt with very carefully. Secondly, there's scope to help students with expressing code problems, for instance by encouraging them to always include the code they wrote, expected output and the actual output, rather than just a general comment stating the code doesn't work. And so for future work, we agree with, again, Kian and Lehman, that there is a lot to be done to understand the challenges and student strategies in more detail, for instance, through the lens of conceptual change theories. We would like to acknowledge all the students who gave permission to use quotes from their discussions. And these have been included in our full 80-page report, which is a companion to our SIGCSE paper. And do get in touch if you would like to receive a copy of the full report.